Hi, this is John Whitaker for the Probability 1 graduate level class, and this is our 7th video lecture. And last time we ended talking about discrete random variables with some specific types, and in particular we ended with the geometric random variables, discrete random variable. And I want to do a generalization of that geometric discrete random variable in terms of just defining it and giving some of its properties. And so here is the definition. So suppose a Bernoulli experiment is performed until the R success occurs, where each experiment is independent let x be the number of times the experiment was done, and that's to get the R success. Then x is called a negative binomial random variable okay. Could be said with parameters R and P, where the probability for success equals to P, and R is the number of successes you want to get. Okay, then as a fact, if x is a negative binomial random variable, with parameters R and P, then the PMF of x is, so it's f of x, and here's what happens. First of all, there were R minus 1 times that you got, you had to get R successes, so you should have P to the R. And really, the last one was a success, okay? So the previous ones, out of the previous ones, the x minus 1, number of times you did it, R minus 1 of them had to be successes. So there are x minus 1, choose R minus 1 ways to put successes in the x minus 1 terms. Then it's p to the r, the number of successes that you had, and then it would be 1 minus p, x minus r, where where x, to get r number of successes, you have to do it to try at least r times. It could be r plus 1, r plus 2, and so forth forever. And so that is the PMF. Now, I called this, when I started this video lecture, an extension or generalization of the geometric random variable. And that's because for the negative binomial, what we're doing is we're going to R success, where really a geometric is where you're going to the first success. Okay? And so the geometric is really a negative binomial with R equal to 1. Some other characteristics that I want to make mention of for the negative binomial. So let's call this facts. Here's one. If x is a negative binomial, random variable, with parameters R and P, then the expected value of x. Okay. So if you remember the expected value of x for a geometric with 1 over p, well, this is going to be R over p. That's the first factor. And 2, the variance of x. If you remember for a geometric, I think the answer was 1 minus p over p squared. For a negative binomial, it's R times 1 minus p over p squared. Okay, so those are those extensions that I was talking about. All right, let us look at a quick example of a negative binomial. So as an example, let's use the same one we have been working with, and that is a card is selected at random from the standard deck. Its suit is noted. And the card is returned to the deck. And the deck is reshuffled. This is done until the 5th heart is obtained. Then x is a, let me say what x is. Let x be the number of times card is drawn fifth part. Then x is a negative binomial, and the PMF of x is, so it's f of x is equal to x minus 1, choose 4, that's r minus 1, r was 5 here. Then it's p, which is 1/4, raised to the r, which is 5, and then 1 minus p, that's 3/4, raised to the x minus 5, where x starts off with 5, 6, it goes on forever. The expected value of x is r over p, which is equal to 5 over 1/4, which equals to 20. So the expected number of times you do this to get the fifth part would be 20 draws. 3, the variance of x, well, that was r times 1 minus p over p squared. That ends up being 5 times, in this case, 3/4 times 1/4 the b squared, whatever number that is. So that's just an example of a negative binomial random variable. And I didn't go through the details of why its characteristics are what they are, but I just wanted you to be aware of them. And that concludes what I needed to talk about for common discrete random variables. So the next thing I want to do is start talking about continuous random variables, what they are, examples of them, how we're going to find the expected value, what function it has related to it. Instead of a probability mass function, it's going to have something else, what its characteristics are going to be. So let's talk about continuous random variables. So here's the definition. So first of all, when we're talking about continuous random variables, what we're talking about is a random variable that can take on more than, or can take on uncountably many outcomes. But this is the way we're going to define it. So as a definition, x is a continuous random variable if there exists a non-negative function f of x defined on minus infinity to infinity, the whole real line, such that for any subset of the real line, the probability that the random variable x is in, its output values are in B, is equal to an integral over B of f of x dx. That's the way it's defined. It's a non-negative function, and qualities it has. That's the definition for continuous function. Let me say one more thing, excuse me. In this case, f of x is called the probability density function of x. Okay? So a continuous random variable has a probability density function discrete random variable has a probability mass function. Okay. So a fact is that if f of x is a probability density function, which we'll abbreviate PDF, of a continuous random variable, x, then the interval from minus infinity to infinity of f of x dx, well, that has to be equal to 1. And the proof of this fact, if we let f of x be the PDF of x, then here's the first thing I know. 1 is equal to the probability that x is an element of minus infinity to infinity. So what does x do? X is a random variable, so it grabs outcomes of experiments and associates to them real numbers. So the chance that x of something is a real number, that's 100%, okay, or 1. And how would we compute this probability? Well, by the definition of it being a continuous random variable, it should be from minus infinity to infinity, that's what v is in this case, of f of x dx. And so we have that this interval is equal to 1. That's the proof. Some other facts that come just from the definition of the probability density function, I'll list next. And that is, so here is a fact for a continuous random variable. Let's call it facts. For a continuous random variable x whose PDF is f of x, then, so the first fact is the probability that a is less than or equal to x is less than or equal to b is equal to the interval from a to b of f of x dx. And that's straight from the definition. And 2, the probability that x equals to a, that's really the probability that a is less than or equal to x is less than or equal to a, is equal to the interval from a to a of f of x. And the interval from a to a of f of x dx, that's going to be equal to 0. And that's an interesting fact. That means that for a continuous random variable, the probability that that particular random variable is equal to a particular number is 0. Let's look at an example for a continuous random variable, one we've already seen. And I'll refer to this example several times. So a person will arrive at random at a bus stop between 5 p.m. and 5:30 p.m. Let x be the time after 5 that the person shows up. Then x is a continuous random variable. And in particular, with PDF, f of x equaling to, well, it would be 1 over 30 if x is an element from 0 to 30, and it would be 0 otherwise. Okay, so here, let me write this a little better. You see x is an element of 0 to 30. Let's see, can you see that? No. Yeah, I think you can. Okay. All right, so that's what it is. Okay. Well, we want to find what an expected value is for a continuous random variable. So here's that definition. If x is a continuous random variable, with PDF f of x, then the expected value of x is denoted by e of x and given by e of x is equal to the integral from minus infinity to infinity of x times f of x dx. So that's the expected value of x. And this is an improper integral, but a lot of times I'll be a little sloppy. Instead of writing limits involved here for this improper integral, I'll just be a little bit sloppy in computing the expected value of x. As an example, consider the bus stop example, where the person will show up at random every time is equally likely between between 5 and 5:30, and x is the amount of time after 5 that they show up. And so when I said that, I mean x could be any time, like 1.333333, or the square root of 2, that number of minutes after 5 o'clock. And so anyway, x is the time after 5 the person shows up, arrives, and then let's compute the expected value of x. So the expected value of x will be equal to the integral from minus infinity to infinity of x times f of x dx. Now, this is equal to, really, the integral from minus infinity to 0 of x times f of x dx plus the integral from 0 to 30 of x times f of x dx plus the integral from 30 to infinity of x times f of x dx. And I won't break things down into this way very often, but the reason I'm breaking them down is recalling what f of x was, is the probability density function. Remember, it was defined to be 0 a lot of the times, and the only time when it wasn't 0 is when x was between 0 and 30. And so I broke it, this integral from minus infinity to infinity to these three different intervals, because I can, and by doing so, over this region, from minus infinity to 0, f of x is 0, and so 0 times x is 0, the integral of 0 dx is just 0, so this is equal to 0 plus the integral from 0 to 30 of x times 1 over 30 dx plus, this guy's going to be 0 because f of x is 0 for this part. And so this ends up being 1 over 30 times x squared over 2. You remember by the integration, we want to evaluate that from 0 to 30. And then when we stick in 30 for using the fundamental theorem of calculus, when we stick in 30 here, we get 30 squared minus 1 over 30 times what we get when we stick in 0. Oh, it's 30 squared over 2. Don't forget that. And this is going to be 0 squared over 2. And so our answer here is, it looks like it's 15. Minus 0, so that's just 15. That makes a lot of sense. So the expected value is supposed to be the average. And on average, if that person shows up any time between 5 and 5:30, on average, we expect them to be there around 5:15. And so 15 minutes after 5, that's what we found for the expected value of x. Okay, so another thing we're going to be interested in is how to define the expected value. So this is the definition. The expected value of a function of x. So let x be a continuous random variable. And this is similar to what we did before. It's exactly the same. Oops. With PDF f of x and let g of x be a function of x. Then the expected value of g of x is, so it's the expected value of g of x, which is equal to the integral from minus infinity to infinity of g of little x times f of x dx. Let's look at an example of that. We'll stay with that bus stop example. So, consider the bus stop example where x is the amount of time after 5 person arrives. And let's say someone asks, what's the expected value? So find the expected value of x cubed minus 2x plus 1. Okay, so the way we do this is, well, the expected value of x cubed minus 2x plus 1 will be equal to, it'd be the integral from minus infinity to infinity of x cubed minus 2x plus 1, that's g of x, times f of x dx, which, because f of x is only non-zero in the region from the x values from 0 to 30, we can say this same thing is the integral from 0 to 30 of x cubed minus 2x plus 1 times 1/30 dx. So that's what we have to calculate. Okay, and that's equal to, well, an antiderivative for this is x to the 4th over 4 minus, it would be x squared plus x, all this times 1/30, and we're going to evaluate it from 0, as x goes from 0 to 30. And so that's equal to 30 to the 4th power over 4 minus 30 squared plus 30, and then all that to be multiplied by 1/30, and you would subtract from that what you would get when you stick in 0 for x, but that's just 0. And so the answer, I did this, and I believe the answer is supposed to be 6,721. That's what we get. Okay, the next thing I want to do is define the variance for a continuous random variable. So let x be a continuous random variable. Then the variance of x it's denoted by VAR of x as we did before, and what it's equal to, just like what we had before, is the expected value of x minus the expected value of x to be squared. Okay? So that's exactly the way we define it for a discrete random variable. And we had a fact that helped us calculate the variances, and that same fact is going to apply for continuous random variables as it did for discrete random variables. Okay. Namely, my screen isn't very focused. Let's see, was it focused before over here? Hello. Focusing? I think so. Sorry about that. I hope the word here is clear to you. Okay. It's a fact. We have that the variance, if x is continuous, then the variance of x is equal to the expected value of x squared minus the expected value of x to be squared. We want to prove this. So here's the proof. We let x be a continuous random variable. Then the variance of x equals to the expected value of the quantity x minus the expected value of x to be squared, which will be equal to the expected value of the quantity x squared minus 2 times x times the expected value of x, and then plus the expected value of x to be squared. The expected value of x is going to be a number. Now, using our definition of how we take the expected value of a function of x, and so this x squared minus 2x times the expected value of x plus the expected value of x to be squared, that's a function of the random variable x. Okay, that is going to be equal to the integral from minus infinity to infinity of x squared minus 2x expected value of x plus the expected value of x to be squared. All of that is to be multiplied by f of x, which is the probability density function, dx. All right, we could break that up into several intervals. It's the interval from minus infinity to infinity. Here we're going to have, well, let's write it down as one interval at this point, where I distribute the f of x. And we can rewrite this as several intervals being added together. So it's from minus infinity to infinity of x squared f of x dx minus the integral of 2x expected value of x f of x dx, and then plus finally the integral from minus infinity to infinity. This was from minus infinity to infinity of the expected value of x, all that to be squared, f of x dx. Okay. I think you can see it, f of x dx. This is equal to, this first interval is the expected value of x squared minus, the expected value of x is constant, so it's 2, so I pulled it out of the interval. This becomes the interval from minus infinity to infinity of x f of x dx. And that's plus, here, the expected value of x to be squared is going to be a constant, so I can pull it out. Integral from minus infinity to infinity of f of x dx. And so here, this is equal to the expected value of x squared, we're not messing with it, minus 2 times the expected value of x. And what this integral is, it's nothing more than the expected value of x plus, this is the expected value of x to be squared, but here we're multiplying it by the integral from minus infinity to infinity of f of x dx, and one of the properties we have is that that integral is equal to 1. That's one of the properties of a probability density function. Okay, and so we'll finish up this proof. Almost done. And so what that's equal to is the expected value of x squared and then minus 2 times the expected value of x to b squared plus the expected value of x to b squared. And so that ends up giving us the formula that we were looking for, or we said was true. That's the proof. Okay, as an example where we're finding the variance, let's consider the bus stop example. Okay, and we know x is the time after 5 o'clock that the person arrived. The variance of x is equal to the expected value of x squared minus the expected value of x to b squared. Remember, we calculated this earlier. The expected value of x was 15. So we need to know what the expected value of x squared is. So note the expected value of x squared. That's going to be equal to the integral from minus infinity to infinity of x squared times f of x dx. Remember, f of x is the PDF, which was defined to be 0 a lot of times. The times that it wasn't 0 is when x was in between 0 and 30. So this ends up being the integral from 0 to 30 of x squared times 1 over 30 dx, which is equal to x cubed over 3 times 1 over 30, and I need to evaluate that from 0 to 30. And then we'll only get some answer when I stick at 30, so it's 30 to b cubed over 3 times 30. That ends up being 300. Okay, so we're ready to get to the variance now. Very close to having it. So, the variance of this particular x, which is the expected value of x squared minus the expected value of x to b squared, that's going to be equal to 300 minus 15 squared. So that's 300 minus 225, and that is 75. Example. Ladies and gentlemen, what I want to do next is talk about some common continuous random variables. And the first one I'm going to start off with is a uniform random variable. And so here's a definition. A continuous random variable x is said to be uniformly distributed uniform random variable on A to B, where A and B are real numbers, if the PDF x is f of x equal to, well, it's 1 over b minus a if x is an element of a to b and it's 0 otherwise. That's what our bus stop example was. Okay? And so we want to talk about some facts about that. But the first one I want to do is that if you remember the integral from minus infinity. So here I'll just say this. Note the integral from minus infinity to infinity of f of x dx, if we have a uniform random variable, is going to be equal to the integral from minus infinity. Well, it's only going to be non-zero from a to b. So this will be 1 over b minus a dx. And that's going to be equal to 1 over b minus a times x, evaluate from a to b, which is going to be 1 over b minus a times b minus 1 over b minus a times a, which equals to b minus a over b minus a, which of course is 1. And that's one of the facts about a probability density function. When you integrate it, you better get 1 when you integrate it over a line. We'll look at least one more aspect for a continuous random variable. That is, we'll look at its expected value. So, as a fact, if x is a uniform random variable, continuous random variable, on a to b, then the expected value of x is equal to b plus a over 2. And so let us prove this. So the expected value of x for it being uniform, remember, that's going to be equal to the integral from minus infinity to infinity of x f times PDF, f of x dx, which is going to be equal to, well, f of x is 0 a lot of spots. The only spot that's not is from a to b. X and over a to b, f of x is 1 over b minus a dx. This ends up being the antiderivative, x squared over 2 times 1 over b minus a. I need to stick in 4x, the value is a to b. And so what I get is b squared over 2 times b minus a minus a squared over 2 times b minus a, which equals to b squared minus a squared over 2 times b minus a, which of course this top factors, it factors b minus a times b plus a over 2 times b minus a. And the b minus a's cancel, and so we're just left with b plus a over 2. And that's what we said the answer was going to be. So that's the proof. And, well, we have time to do the variance, so let's go ahead and handle that. So, as a fact, if x is uniformly distributed, continuous random variable, on A to B, then the variance of x is equal to, it is b minus a to b squared over 12. That's the fact that happened. Let's prove it. And so, remember, the variance of x by formula is equal to the expected value of x squared minus the expected value of x to b squared. We just found this. So, we need to find the expected value of x squared, which is going to be equal to the integral. In this case, it's going to be from a to b of x squared, 1 over b minus a dx, which is going to be equal to, so here's x cubed over 3, and then b minus a is in the bottom. We want to evaluate that from a to b, which ends up being, so it's b cubed minus a cubed over 3 times b minus a. Now it turns out the b cubed minus a cubed, that factors is b minus a times it's b squared plus ab plus a squared over 3 times b minus a. The b minus a's will cancel. The b minus a's would cancel, and we'd just be left with equal to b squared plus ab plus a squared over 3. That's what the expected value of x squared was. So the variance of x is equal to the expected value of x squared minus the expected value of x to b squared would be equal to this b squared plus ab plus a squared all over 3 minus, remember this was b plus a over 2, but that's the b squared. So this ends up being b squared plus ab plus a squared over 3 minus, this is going to be b squared plus 2ab plus a squared all over 4. So the common denominator here is 12. So what we end up getting is 4b squared plus 4ab plus 4a squared. Then this would be minus 3b squared, multiplying everything by 3. So this would be minus 6ab. And this would be minus 3a squared. And I've run out of room, but we're almost done. Okay, maybe I have a little room here. This is equal to, now. So simplifying that, what we're going to get is a b squared minus 2ab, and then it is plus a squared, and that's over 12, and then that ends up being this top factors, it's b minus a to b squared over 12, and that's what we said. All right, ladies and gentlemen, that's enough for this video lecture. Thank you very much for your time and patience.